Hello, this is the last part of the integer linear programming lecture. In this lecture, we're going to look at how to solve linear integer programs using branch and bound method. Consider the following linear program, integer linear program. Very simple, two decision variables, objective function, three constraints. However, both decision variables are non-negative and integers. So if we solve this problem, if we treat this problem just like a linear program, ignoring the integrality requirement or constraint, we call this LP relaxation. That means we forget about the integer requirements for a second and solve it just like a regular LP. We solve this integer LP just like a regular LP. And the solution comes out to be, in this case, it could be integer, by luck, but usually it is a continuous solution where x1 in this particular problem came out to be 2.5 and x2 1.5, and the z value is 10.5. Obviously, the problem needs to be integer, but this is not integer solution. Z doesn't have to be integer because the decision variables have to be integers, but z can be anything. It doesn't have to be integer for the linear integer program. Okay. Let's look at the graphical solution. This is what we just solved in the previous slide, and the optimal solution lies at this corner where x1 is 2.5 and x2 is 1.5 and z, as I said, is like 10.5. However, this is not the right solution for this problem because both decision variables are not integers. So what do? We could simply round up, meaning that we assume instead of x1 star being 2.5, we could treat it to be 3, rounding up, and x2 star is 1.5, we could treat it to be 2. So the integer solution for this problem becomes x1 equal to 3 and x2 equal to 2 by rounding up. However, if you look at the feasible region in the next slide, you're going to see that both this solution, x13 and x22, actually falls outside the feasible region, which makes this solution to be infeasible actually altogether, not feasible. Here's where this solution lies, 3 and 2, x1 equal to 3, x2 equal to 2, which means it lies outside the feasible region. So that means it's not a good solution. So rounding up in this particular problem seems to be not a good idea because you are altogether outside the feasible region. So let's try rounding down. Rounding down, instead of x1 equal 2.5, it becomes 2, and instead of x2 equal 1.5, we round down to 1. Okay, this falls inside the feasible region, as we will see in the next slide. And the z function, if you substitute x1 equal to 2 and x2 equal to 1, the z becomes 8. Now the question, this is an integer, a feasible integer solution. However, it may not necessarily be optimal because this is a very simple problem. I can guess it out. I can guess the solution. The solution is going to be x1 equal to 3 and x2 equal to 0, which is integer obviously. And if you plug these into the z function, the z becomes 9, which is larger than 8, which means that rounding down wasn't also a good strategy. It did not provide the optimal solution either. So there must be a better way to find the optimal solution by rounding up and down. And here's an exhaustive list of the solutions for this very simple integer problem, because I know z is going to be 0, 1, 2, or 3. So I list 0, 1, 2, 3 for x1. Sorry, x1 needs to be 0, 1, 2, 3, not z. And so at 0, 0, so it's like I'm looking at the graphical solution. I'm taking the grid solution. That means every point on the grid, 0, 0, z is 0, x1 is 1, x2 is 0, the solution is 3, and so on. You can find out by exhaustively enumerating all possible solutions, integer solutions to the problem, and calculating the value of z. You're going to find out that z is the largest or the most when x1 equals to 3 and x2 equal to 0, and thus this is the optimal solution. So here in this exhaustive list of solutions, I only considered grid solutions that they fall on the grid in the graphical solution and that are inside the feasible region, and did not consider obviously the points on the grid that are outside the feasible solution. And here's the points that I considered in the previous problem or the previous list. In the previous slide, you're going to see 0, 0 solution, 1, 0, 2, 0, 3, 0, and then 0, 1, 1, 1, 2, 1. Here you cannot have a 3, 3, 1 because it's outside the feasible region. And there's here one solution which is 1, 2. Oh, those are all the solutions on the grid that are integers and that are inside the feasible region. As I said, we cannot rely on rounding up and down to find the exact optimal solution for these integer linear programs. So if I'm really insist on finding the real optimal solution, integer solution for these integer problems, then I have to deal with it as an integer problem from the beginning. And the most popular and successful way of doing that is called the branch and bound method. In branch and bound, we first find the problem solution. We find a solution to the problem for the relaxed problem, and then from there I start branching for various problems. So I have to solve the problem multiple times using the simplex method, adding constraints subsequently as I solve more and more of these problems. We will see this in the next few slides. So as I said, the first step is to solve the problem as a relaxed LP problem. That means I relax the constraint of integrality constraint, relaxing the integer constraints. That means I just assume that x1 and x2 or all the decision variables can take any values they want. Doesn't have to be integers. This is called the relaxed version of the problem, or the relaxed problem. This will in general produce continuous range. Obviously, if you solve a problem that way without ignoring the integrality constraint, and you get the answer to be integers for the decision variables, then you're by luck you arrived at the right answer for the integer problem. But usually you will not get an integer solution for all the decision variables. Okay, in that case we have to do the following. We take one of these variables and constrain it to the values above it and below its current value. That means we branch on that decision variable. So we add two new constraints, or two constraints for two new problems, and we solve these problems that we just defined by branching on one of the decision variables. We're going to see that in the next slide. Let's assume this is a problem. Here's a linear integer program, and the solution for this problem, the optimal solution, is x1 equals 3.75 and x2 is 1.25. So that's the solution of the relaxed problem. Now I need to take one of these solutions, the x1 equal 3.75 or the x2 equal 1.25, and branch on it. Branch on it meaning that I add two constraints, and I define two problems by adding an extra constraint. One of the constraints for the first problem would be x1 is less than 3. You see, I take the integer value below the current value and the integer value above the current value of that decision variable, which I'm going to call it the branching variable. So I will add one constraint, call it x1 less than 3, and add another constraint, call it x1 larger than 4. So the value below it and the value above the current continuous solution. And thus I define two new problems. I will solve them separately. Okay, so let's see what happens when I do that. Here's one problem I solve with x1 less than 3, and another problem I solve by adding this constraint x1 larger than 4, and then I solve these two problems. And I continue branching on one of these decision variables until I get a solution where it is integer. That's, in a nutshell, the branch and bound technique. Let's see the details of it next. So to do the branch and bound efficiently, we follow a binary tree structure, and every node in that tree represents a problem, a specific problem to be solved, and then the branches of that problem will be the branching variables that I talked about, which I need to define new problems to be solved using the simplex method. Okay, so to reduce computing time, we try to keep the number of nodes in the tree as small as possible, obviously, if we can. So there are two strategies that I can solve this binary tree problems: the depth first strategy and the breadth first strategy. For those people who had taken courses in data structures, this becomes easy for them. So you want to explore the tree, or you want to solve the problems associated with this tree using either depth first strategy. That means, I will go through all the branches from top to down, or the breadth first strategy, where I can go through the branches along one level of the hierarchy, horizontally across one level of the hierarchy. Okay, we'll see that in a second too. Okay, so the depth first strategy takes the left hand branch until the tree can be pruned. That means, you cannot go down any further. So we take the left hand. It's by convention you go with the left. You could take the right hand, but by convention we all agreed that let's take the left hand first, so we all can arrive to the same solution the same way. So let's take the left hand side of the tree, and then it backtracks to the last node where it could take another branch. So once you reach the lowest level in that tree, using taking the left hand side until you cannot go down any further, then you back up one level in the tree and you continue to another branch to the right of that point that you have reached. Okay, then it continues with left branches. Then you continue with the left branches in the once you go down into this higher levels of the tree. In the breadth first strategy, the breadth first strategy evaluates all nodes at level 2, meaning like level 1 is the apex, the one first node that we created for the relaxed problem. So level 2, that means all the problems below it. So we go from left to right, solving all these problems at that level 2 hierarchy. So we don't go down as we did in the previous slide with the depth first strategy. Okay, so and then we evaluate all nodes at level 3 and then level 4 and so on. Okay, on average it has been found that depth first strategies are faster than breadth first strategies. That means on average it has been found that depth first strategies can arrive at a solution, optimal solution for the integer program, faster than the breadth first strategies. However, there's no proof for this, and sometimes this rule is broken, and as we will see in the example that we will solve in this lecture. But however, in general, it's been shown experimentally, and there's not a proof for it, because obviously it doesn't work all the time, that depth first strategy is a better way for solving linear integer programs using the branch and bound technique. This is an example which we'll solve completely in the rest of this lecture. This example is maximize 4x1 z equal 4x1 plus 6x2 plus 10x3, and subject to 1, 2 constraints, and the last integrality constraint says that all decision variables x1, x2, x3 are non-negative, and there must be integers. Okay. Now, as I said, we will branch left down. So we're going to use the depth first strategy, taking the most left branch on the non-integer variable. So we branch only on the non-integer variables, by the way. So if a variable is integer, we cannot branch on it. So we branch on non-integer variables with the lowest subscript. Again, this is by convention. So we're going to use the lowest subscript decision variable that has a non-integer optimal value. We'll use that as a branching variable. Okay, that means if I have x1 and x2 both are non-integers for a particular solution, for a particular problem, I will take x1 as my branching variable. Now, however, if x1 turns out to be an integer solution for the problem, but x2 is not an integer solution, then I will branch in this case on x2 because it's the next highest subscript after the lowest one. Okay. So the first thing I did here is I solved the problem in the previous slide, and the answer was x1 4.71, x2 equal 3.57. Obviously, this is the top of the binary tree that I use for branching, and this solution is for for the relaxed problem. As we said, we just solved the problem as a regular linear program. And notice here that x1 is non-integer, x2 is non-integer, x3 is an integer, x3 is 0. So it's possible that you get an integer solution for one of the variables. So this decision variable has an integer solution, while the other two, x1 and x2, have a non-integer solution. Obviously, if by luck I get all the solutions to be integers, x1 is an integer, x2 is an integer, and x3 is an integer, I stop. This is the optimal solution for the integer problem, by the way. Okay, but usually we don't. So one of the variables will be integer. So the rule says let's branch. We're gonna use depth first strategy. So depth first, we're gonna go down and not breadth. Breadth you use level 2 like this, and level 3 so we solve this problem. But here no, we're gonna go depth, going to branching on the lowest indexed variable. Lowest index variable if it is non-integer. Obviously, the lowest index variable here, x2, x1, x2, x3 are all these indexed variables. The lowest index is x1. The index is 1, the index is 2, the index is 3 here for x1, x2, x3. That's it. So we'll go to the lowest index variable is x1. Is it integer? No, it's not integer, so I use it. So the lowest non-integer, the lowest index variable which is non-integer, it seems to be x1 is the lowest integer value, is the lowest indexed variable that is not an integer, and I branch on it, and I take the left branch. So here I said, okay, how do I branch on this? As I said earlier, it's smaller than the integer value of that variable, and larger than the rounding up the integer value. So it's smaller than 4 and larger than 5. So one branch is x1 smaller than 4, and another branch is x1 larger than 5. But because I'm branching to the left, depth first strategy, that means I will solve this problem. This problem I will not solve. If I am doing depth first strategy, breadth first strategy, then I will define this problem and I solve it. I solve this, then that, and this is a level 2. But I'm not doing that. So I define a new problem. It's exactly the same problem that I had before, but I add a new constraint, which is x1 less than 4. So now I have 3 constraints instead of 2, just like what I did solve this problem without any constraint. I add to it this constraint, and I solve it. And the solution to this problem turns out to be x1 equal to 4. Notice here that now x1 became integer, and x2 is 2.5 and x3 is 0. Great, so I have 2 integers, but still I have x2 is non-integer solution. That means I still don't have an optimal solution for the integer problem. But so how do I branch now? It says the lowest indexed variable. This is the lowest index variable that has a non-integer solution. Okay, x1, this is the lowest index variable, but it has an integer solution, so I go to the next one. x2 is the next lowest index variable that has a non-integer solution, so that means I will branch on x2 now. How do I branch on x2? I will define 2 constraints. One constraint as it will be less than the lower value when you round down, and another constraint when it is higher than rounding up value. So I will add the constraint x2 less than 2 and x2 larger than 3. Okay, so and I go down. So here's what I meant when I said branching down most left. So you can notice that I'm going down to the left, most left. Okay, by convention again. So I ignored this problem earlier on, and now I will solve this problem and I ignore that problem. So I add now another constraint x2 less than 2 to the problem that I just solved with x1. So the original problem, I added one constraint x1 less than 4. Now I add another constraint x2 less than 2. So x1 is less than 4 and x2 is less than 2. 2 new constraints that go into this problem, and then I solve it, and then I get an answer. Obviously, I'm solving it using the simplex method or Excel or whatever software that you have, but you're completely solving the problem from scratch. And that takes a lot of time. That's why branch and bound takes a lot of time. So far I've solved one problem for the relaxed problem, another problem, and this is the third problem I'm solving, and the answer became x, or came back to be x1 equal to 4, x2 equal to 2. Great. So two integer, however, x3 all of a sudden became 0.25 non-integer. Okay, so I will branch on this. This is the only non-integer decision variable, and branch on it less than 0, but we don't have less than 0, so it's really equal to 0. And x3, so one branch is x3 less than or equal to 0, but it cannot be, it must be equal to 0, but we have x3 less than 0, and x3 larger than or equal to 1, x3 larger than or equal to 1. So I have this problem. Now I solve this problem as the fourth problem. Remember, I solved one problem, two problems, three problems, and this is the fourth problem I solved. The fourth problem that I solved, I have x1 equal to 4. The solution came out to be x1 equal to 4, x2 equal to 2, x3 equal to 0. Perfect. All integer solutions. This is a feasible, I'm not sure if it's optimal yet, but this is definitely a feasible integer solution for the integer problem with a z value. If I substitute this solution in the z function, I get z equal 28. So the first feasible integer solution is x1 equal to 4, x2 equal to 2, and x3 equal to 0 with z equal 28. This is a feasible solution, but not necessarily optimal. I will take this as a lower bound or an upper bound. So this is a lower bound because you cannot do worse than this. Okay, we call this a lower bound. That means the optimal solution, whatever optimal solution you get, is not going to be worse than this. So z equal 28 is your lower bound. What's your upper bound though? The upper bound is right here. You're never going to be better than 40.28. So if you get an answer better than that, it's impossible, because the biggest answer or the largest answer you get for any linear integer program is the relaxed solution. So this relaxed solution is the best answer for the integer problem. Now once you start adding constraints, the z value definitely would have to go down. At best it'll stay the same. So I do not expect, when I solve a problem at the lower hierarchy, I do not expect to get larger value than this z. I may get the same value or less. And that, you can see that the lower value of z is going to be less than 31, yes, less than, and the lowest value here is z4 is 28, less than that. And if you go down further, you will also get less. So that means here, since we have all integer solutions and you get a z value, then this is basically your lower bound, because you're not going to get worse than this. And your upper bound is the unconstrained solution, which is we call the relaxed version or relaxed problem, that you will not get better than that. And obviously this is for a maximization problem. And for a minimization problem, you will flip that logic. So this becomes the lower bound. Okay, and this is the upper bound. For maximization problem, this is the upper bound, and this is the lower bound. Okay, which means what? Which means that if I go and solve a problem in other branches of this tree higher than this level, they will have actually a better z value. And if they're integer solution, then this means this is a better solution. That's why this is the lower bound. I may get better solutions, but I will not get worse solution than this. Okay, so if I get any value for solving the problem in other branches of the tree here that I haven't really solved yet, but I'm going to solve later. If I get the value less than 28, I don't bother going through that branch of the tree, because I'll say, no, I already have a better value here. Okay, so that's the approach. Now, what does the method? How does the method continue after you find a? So after we find an integer solution for a branch in a tree, like here, this is the most left. I stop. I do not go any further. There's no branching variable anymore. So I stop here, and this becomes one of the lower bounds. Okay, so it's a lower bound. So now the method goes back. It goes backtrack to the upper level, and continue to the right. And then obviously, if there are more branches here, I continue to the left. Okay, so I backtrack one level, take the right branch, and then continue to the left. So I backtrack one level, and now I go to the right, and now I have another problem with x3 larger than 1. So I add a different constraint, which is, so this constraint is not existent anymore. Only this and that, the x1 less than 4, x less than 2, and x3 larger than 1, and I solve the problem, and I will get a solution here. Okay, and then either I continue I continue branching down left, or if I get something less than 28, I don't even bother to continue. So then I branch up, I'll check, I say, well, I already solved this, there's no right, so I go back up again, and then I go to the right here, and then I solve this one. Okay, and then I branch down if necessary until I get to a place where either I have a solution less than 28, I don't go down any further, and then I backtrack here, and I take this branch and I solve this problem now, and I get some answers, and that's how it works. So in the previous tree that we've seen, node N1 is the ILP solution, the relaxed version, and it presents an upper bound, as I said. So okay, so always the relaxed problem represents an upper bound to the integer programming problem. As we move through nodes N2 and 3, that means level N2 and N3 and N4, we added more and more constraints on the variables, and thus it means that the z-value will be less and less and less as we go down, never increases. Okay, node N4 is the first node we have found an all integer variable. We'll call this a lower bound, as I said, because you could do better somewhere in the other parts of the tree, but we'll have to check. When we reach such a solution, that means it's an all integer solution, we have reached a bound, we call this a bound. Okay, there's a lower bound in the branch and bound technique. Other branches, we have not yet explored all the possibilities near the LP solution, because as I told you, I have to backtrack to different higher levels. We now backtrack and explore some of the possibilities in the right hand branches, which I showed you how to do that. Okay, now let's look at some of the results. Okay, so in the last slide I showed you this branch and bound. I was here, and then I backtracked and I came here and I solved this problem. Solve this problem, I get x1 equal to 4, x2 equal to 0.5, and x3 equal to 1, so I could branch here on x2, meaning that I have to say x2 is less than 0, which is basically 0, less than or equal to 0, and x2 larger than 1, and I continue going that way. Okay, so I'll continue to solve that problem. Once I'm done, so okay, then I can backtrack all the way to this level and go x2 larger than 3 and solve this problem, and I find out there's no feasible solution, so I stop. There's nothing to do here. And then I go up again, solve this problem. I end up with x1 equal to 5, x2 equal to 3, and x3 equal to 0. Notice here that the solution came to be integer 5, 3, 0, and z is 38, which is much larger than that. So this is a new lower bound. Actually, this is the optimal solution because it's right after the relaxed problem. And branches here will never be better than this, because as I told you, the z-value is going to be less than 29 going down this way, so this is a better problem. So the optimal solution to this problem is really x1 equal to 5, x2 equal to 3, and x3 equal to 0, and z-value is 38. Okay, and here's in this example, if had I have gone with the strategy breadth first strategy, that means I could have started the problem, solved this, and then that I could have found the solution from the second step. I'm still on this level without going through all these troubles. But as I said, by convention we agreed that we're going to go with a depth first strategy, and not breadth-first strategy, because the depth-first strategy works well. In most situations, it finds the solution faster for the integer program, but this is a counterexample where breadth-first strategy was a better strategy and it found the solution much faster than that. But anyway, we wouldn't know that until we actually do it. But this is the optimal solution for this particular problem, okay? Node N5 has all integer solutions, so we do not branch any further from this, as we just showed you. Okay, node N6 is node N6 is infeasible, as I told you, and node N7 does not allow further branches. Notice that Z5 equal to 38 and Z7 equal to 29, and that's why Z5 is the optimal solution, as I told you, because it's better than to that. So there's no need to branch down. If we have evaluated node 5 N5 before N7, we need not have proceeded any further. I told you this already, since it would have been impossible to get a better value. Okay, and this is called fathoming. That means you don't go into that direction in the tree.